Cascadia is hosting campus garden workshops for our campus community to learn and enjoy about campus gardening and gardening at home. Today we're covering soil biogeochemistry with Professor Midori Sakura.
Stefan and I were like talking about, titles and different topics and so forth. One of the things that I thought was really important to talk about was this, not only soil, but actually the more complex portion of soil that is not just the inert, material that most people would, think of, like, oh, just, this dirt, basically, right? So I made this kind of, just because I don't have a PowerPoint out here, I have no slides, and I wanted to show some words. So one thing is, and for a lot of people, they wouldn't necessarily associate how complex soils are, or that, there's this, I intentionally try to put, biogeochemistry out here, because bio, think of life, right? Living organisms, and what are they doing to change and modify the soil, and why is it different with their activity in there? And then geo, we think about rocks and, like these kind of like non-living components. And then chemistry, actually. There's a ton of chemical reactions that go on in soils. And so I actually, for those of you who don't know me, I'm actually a bona fide soil scientist. My degrees are in soil science. I'm actually a certified professional soil scientist. There is, last I looked, which was a couple years ago, but I think there are like 28 certified professional soil scientists in the state of Washington. But suffice to say is that, like, soil science is this really, in my really strong opinion, the most dismissed system, the most misunderstood. It's totally out of sight, out of mind. People are way more interested in outer space and plants and things with, wings and legs, and things that are running through the field. And so we tend to focus on from the surface up, and yet, like, everything on the surface up is being influenced by what's underneath our feet. It's the interface between the atmosphere and life, and it's where water's running through, and most of our food grows in the soil, and our houses are on it, and this is where we get our groundwater from, and everything is connected to it. But it's like the system that most people don't pay any attention to, right? You're not people aren't running around with a shovel and on a hike and so forth, and I'm kind of geeking out on looking at soil layers and so forth, because they tell a lot of information. For most people, they call it dirt, right? It's not even like it's something that we kind of shun, especially in our cultures. A lot of societies really embrace soil, but there's a lot of cultures that are really like have a phobia almost of like getting their hands dirty and so forth. So it's this really misunderstood system, and it's also really importantly, it's so incredibly complex. Chemistry is at the backbone of soil science. So it's so much more complex than people give any credit for, and it's just not this like, dirt, this inner material that's been there and always will be, and they don't understand, like, this had to form actually, and it doesn't form on our timeline. It's not on a human timeline. So the whole issue about like sustainability practices and how we farm and how we grow plants is really critical, actually, because we don't have much good soil that grows plants naturally, and so we end up having to put tons of fertilizers, and we tend to grow like lots of monocultures and things that are pretty hard on the soil. And I realized, so I'm giving 2 talks. This is going to be soil biogeochemistry, so it was actually really hard to kind of separate the two the more I delved into it. I'm going to try my best not to overlap too much, and if I do a little bit, I'm just throwing some chum at you to like get you to come to the second one, because I'm going to talk a lot more about fertilizers, pesticides, and nutrients in the second talk. So what I really wanted to do in this talk was to really focus on this mysterious big word, fancy word, right? Because when you throw living organisms in with this, the inert soil particles, the geology portion of this, and you mix in chemistry, you sort of get this like really crazy complex situation that is far different than anything, the average layperson would actually consider, okay? So I'm going to focus largely on that, and what's really going to separate this talk from, especially from like the next talk and so forth, some other things you might hear, is the bio portion. Talking about living organisms, and I'm also really going to focus a lot on because I know this is really a garden talk. So I want to gear it towards, plant life and crops and so forth, and how that's really influenced by this particular aspect. There are 5 soil forming factors, and these are official soil forming factors. They're very broad in nature, but when we start thinking about how do soils develop, why is there so much variability and diversity? Because we can actually dig a hole here, a hole there, a hole there, and we would find different stuff going on. And especially if we start going on a hillside or different areas, we're going to find a lot of variability. So there's actually 5 soil forming factors, and they are paramaterial, topography, climate, the biotic community or biological organisms. So when you hear bio, you think living organisms like biology, and time. And these are not in any particular hierarchy. There's no, there's not an order to this. But it turns out when you take all of these, and if you ever have made a smoothie or something, and you get all these different ingredients, you put them in a blender, right? And you modify just one little ingredient a little bit, you kind of get a different product, a different smoothie at the end. You can think of these as 5 really big ingredients, and you modify it just a little bit, maybe the amount of water, maybe the temperature, maybe the plant species that is growing there, or whatever. You modify it by just a little bit, then the soil that develops and continues to develop, by the way, it's never done, it's a dynamic thing. The soil that develops is going to be vastly different just by changing one of these little factors. I shouldn't say little, but one of these factors. So the first factor I wanted to just, and we're going to go over these really quickly because really I'm trying to get to the biological portion, but it's hard to talk about the biological portion without at least mentioning this. Okay, so when people think about soils, generally the first thing they think about is kind of just this, I would say inert material, things that not particularly reactive stuff, and that's really far from the truth, actually. So there is this material and these particles that are going to form. And how many of you would say this is soil? No? Why not?
I think of soil as something that you can crumble.
Crumble. So size?
Yeah.
The size,
so,
right?
Yeah.
So this is too big for this to be considered soil. And actually, you're totally right on track, right? When we start getting to smaller pieces, then we're going to start to call it soil. And there are some magic numbers, but I'm not going to worry about that for right now. But suffice to say, this are not soils. They could be soils eventually when the other soil forming factors get involved. But right now, this is not soil. And paramaterial is actually this inorganic portion of the soil. And so when we talk about organic and inorganic, we're not talking about what happens when you go buy an organic apple at the supermarket. That's a totally different system. When we talk about organic and inorganic in science, what we're really referring to is organic meaning carbon-based, was living, isn't living, so forth. That's what we're talking about, okay? So, thank you. So this paramaterial is what we're referring to as this inorganic portion, okay? Not living, wasn't living, etc. But this can actually break down. The other thing I'm going to ask, what do you notice besides the size and shape, what do you notice as being kind of different? Color, yeah. Color is different, right? And it turns out that even though there are a lot of other variables in this, but color is one of the very obvious physical things we can see. And color is telling us actually something, in part, the elements that are involved in this. So if we have a soil that is developing from something like this white colored, okay, portion, versus this, actually let me use this instead, this, we are going to have very, very different soils that are produced. So this is not soil, but if this breaks down small enough, we can get a soil forming from it, okay? And it turns out that stuff like this, like darker colored rocks have a lot of iron and magnesium in them, and this rock, as it breaks down and weathers, it's going to form a soil that is higher in iron and magnesium than something like this. Which means if you're growing plants in there, and your plant needs a lot of iron or magnesium in it, it's probably going to do pretty poorly in something like this without being supplemented, right? So the paramaterial is sort of like the base plate for most soils. Not so much wetland soils, but for the most terrestrial soils and where we're growing most of our crops, this is going to be the base plate. And as that breaks down, it'll form particles that we call sand, silt, and clay. And a lot of people are familiar with sand, right? Silt and clays are also different particle sizes, and it turns out that sands are actually ginormous. They're huge, okay? And if we were to take one sand particle and compare it to the relative size difference of a silt, okay? Sand particle is about the size of a basketball. Silt is about the size of a golf ball, and if we had a tiny little pinprick of like a sewing pin, that would be the size of a clay. Okay? And why is this important? Because the size is going to influence all these other properties, like how water flows, water retention, nutrient availability, and so forth. So the size of the particles, and whether you have a more sandy soil or silty or clay or a mixture, is actually going to influence all the properties, physical and chemical properties of the soil. Okay? Let's get to the bio portion more specifically. So usually I talk about this a little sooner, but this is kind of like gonna, the big difference. And this is really what's gonna separate just your average soil, something that's, we'll call soil, it makes the size, and it's got sand, silt, and clay in it. But what really separates just, a regular kind of average soil from something that's like the bomb for growing plants. That is what we're going to talk about. And what really makes a huge difference is to think about this bio portion and how the living organisms are actually interacting with the geological part, the soils, and what kind of chemical reactions are they doing. So there's biochemistry that's going on. So when we think of biochemistry, we have to think about that those living organisms are actually involved in this. And they're in there and they're doing a whole bunch of different things. Oh, right? Okay? It's like, come on in, we got the bacteria, we got space, and by the way, we have a buffet going on too, right? So once the organic material starts to accumulate, then all these like bacteria and all the fungus and everything, these groups of organisms that need something else to eat, they start coming in. They're gonna flock in here actually, okay? And it starts to become a positive reinforcing cycle, right? Because now all those bacteria, they're coming in, they're not gonna live forever, they're gonna do their own thing, they're gonna die, and it starts becoming this positive reinforcing cycle of starting to enrich the soil. So with time, we could actually get the stuff that's lighter in color, less fertile. It'll start changing if we can allow more organic material to start to accumulate. What you can do in a garden is you can add the compost, your manure and stuff, and enhance it. And then it's like, it's like speeding up the timeline, so to speak, right? If you hold up your structures there, right, we have the above ground, this material, right? But look how much more root material is there. And I guarantee when you pulled it up, even though you were trying to be delicate, you left a lot of the roots there, right? Okay, so what's the difference then, do you think? So we have a different kind, it's like a hair one. Pulling this, we have a different root structure, right? And this is what we call, like, this has a taproot, okay? And a taproot, like carrot, it has other roots coming off of it, but there's a real big difference in this kind of root structure versus this with all the gazillions of little tiny hairs that are coming off of it. So that's what we call a fibrous root system. This is like a tap, and this is a taproot system. And the reason I'm pointing this out is because we oftentimes focus on the above ground material, and that is actually really important because this material is going to die. It's going to feed all those bacteria and fungi that are in the ground. But the really amazing thing is what the roots are actually doing. The roots are an amazingly powerful, unit that is also organic. Okay, and generally speaking, when we think about roots, whatever we see on the above ground, the roots are way more. Especially when we start talking about like trees, like the amount of tree roots compared to the tree biomass is like really skewed. So we tend to focus on the leaves and the branches and the trunk, but actually what's happening, what's really amazing is what's happening where we don't see it, in the ground, okay? And so one of the things that's happening is this material is, of course, decomposing, and the bacteria are super happy, and they're like, yes, golden corrals right there, we got all this food, right? But then the other thing that's really interesting and quite different, what most people don't understand, is that these roots, all these little roots, are like leaky hoses. So as they're growing, the roots are actually sloughing off material and feeding all the bacteria around there. But the other thing that's really amazing that's happening is the roots are actually leaky hoses. They're kind of like bleeding out nutrients and sugars into the surrounding soil. So as this plant is actually photosynthesizing up here, it's it's like this major highway funneling nutrients and carbs and sugars back and forth. These roots are actually bleeding it out into the surrounding soil. Okay, which type of root structure do you think would have a more of an effect at changing and modifying the soil around it? Tap roots or fibrous roots? Fibrous what? Why? Yes. Way more surface area, right? I mean, this seems like really beefy and pronounced, but if you start measuring the surface area of every tiny little hair-like root, and every one of those is a little leaky hose that is bleeding out carbs and sugars and all this kind of stuff, all this stuff that can draw more bacteria in and more fungi into the situation, then what happens over time is the area around the roots starts getting more enriched than even what we call the bulk soil. So the soil really intimately connected with this is actually called the rhizosphere. And the rhizosphere is like super the bomb for plant growth, because it becomes really enriched, and it does actually start to look really dark, full of organic material, full of nutrients, and it's quite different. If we had plants like a plant here, and there was nothing over here, you would see a real distinct difference. The area around this would start to get a lot darker because the roots are leaking out organics and sugars and feeding all those bacteria. So the bacteria are like coming in, they're like, yes, let's go corral right there.